Hi everyone, in the last video we have looked at tight and relatively compact sequences of random variables. This was aimed to address the problem of escaping mass. What I'm going to do now is in two videos to show you that relatively compact and tight are the same notions. This will be useful for weak convergence arguments, and then this in turn will help proving the central limit theorem. First, I need to talk to you about generalized distribution functions. The definition is here. So, a generalized distribution function is a function from R to 0, 1, a function, I'm going to call this G, which goes from R to 0, 1, which has the following properties. It's non-decreasing, it's continuous from the right, so right continuous, and it satisfies following properties. Let's make them these things into arrows. So if I take the limit as x goes to negative infinity of the function, that's of course smaller than or equal than the limit as x goes to positive infinity. These limits exist, and this inequality is due to the non-decreasing property. The main point here is that the left limit is non-negative and the right limit is less than or equal to 1. Now, why do we call this a generalized distribution function? What is a probability distribution function? A probability distribution function always almost have these properties. The difference would be here. For a proper probability distribution, this would be equal and this would be also equal. So the left limit would be 0, the right limit would be 1. Here what I assume is that the left limit is not negative and that the right limit is not larger than 1. Okay, so that's a generalized distribution function. And then the theorem I want to show you, I'm going to call this a lemma, but it's actually a serious theorem. It's going to be a lemma for us. Sometimes it's referred to as Hell's theorem. So if you want to go a little bit more beyond this, then you could look at Hell's theorem. Okay, so it says the following: if we have Gn, a sequence of generalized distribution function, sequence of generalized distribution functions, which could of course be a sequence of proper distribution functions. Any proper distribution function of course satisfies the definition above, so that's also fine. Then the statement is that there is a subsequence which I'm going to call nk, and a generalized distribution function G such that the subsequence, so along this subsequence G and K, along this subsequence we have pointwise convergence to G at all points where G is continuous, at all x's where the limiting thing G is continuous. And there are plenty of such points because G is non-decreasing, so a lot of points will see a continuity in G. Okay, so next I'm going to prove this, and this is going to be a somewhat tricky proof. So let me start with T being a countable dense subset of R. Okay, everybody knows what that means. So any point of R will have a convergence sequence going in T, or if you want, no matter how close you want to be of any point in R, there's going to be something there in T that close. And T is countable, so you can list the elements. I'm actually going to list the elements as x1, x2, x3, and so on. So this is T. Okay, this is the starting point. Also, everybody knows that on the real line, these sets exist. One famous example is the rational numbers. You can pick any countable dense subset here. And in fact, anything I say, I'm going to formulate it in terms of real value distributions and the real numbers here. But much of this can be generalized to various other spaces. For example, the space needs to have a dense subset. It has to be separable. Okay. Now, here is the next step. It's going to take a big amount of drawing now. So what I'm going to do is I'm going to start writing up a big table. So I have this generalized distribution functions G1 and the list of the points in the dense subset x1, x2, x3, and so on and so on. And I'm going to start making a kind of table of the values of G1 and then G2 and G3. So these are the different generalized distribution functions. And I'm taking all of these guys at the first point of this countable subset T, namely x1. Okay, and it goes on. Now on the next row, I'm going to draw or denote G1 of x2, G2 of x2, G3 of x2, and so on and so on. G4 x2, G5 x2, and then G1 of x3, G2 x3, G3 x3, G4 x3, G5 x3, and so on. G1 of x4, G2 of x4, G3 x4, G5 x4, and then this one, G is G4, G5 x4, and so on. Okay. So we're talking about the generalized distribution function, so all of these values, according to the definition, are between 0 and 1. The function is non-decreasing, and so every value is between 0 and 1, which is a compact interval. So out of these first row of numbers, there is going to be a subsequence which converges to some value, which I'm going to call G1. So these first rows along a subsequence, so G n I of 1 as I goes to infinity, G n I of 1 as I goes to infinity taken at x1 will converge to some number G1. So I'm selecting some members of this list of numbers, maybe the first one, maybe the third one, the fourth and the fifth, and so some of them are left out, some of them are selected in a way that we have convergence to some number G1 between 0 and 1, and that's just because any sequence in the closed interval 0, 1 will have a convergent subsequence. So that's what I do first. I have not selected G2, and immediately I'm going to forget about everything G2. So G2 of x2, G2 of x3, and so on, all of them are now neglected. Okay. The next thing I want to do is that I would like to look at the second row out of those which survived. I see the second row except for G2. In the second row, everybody who survived forms a sequence of numbers between 0 and 1, and because 0 and 1 is compact, there's going to be a convergent subsequence there, G n I2, that on x2 will converge to some other number, G2, between 0 and 1. And the rule is that I'm just want to pick some numbers here which will do that. Maybe the first one is not selected, but maybe the third, fourth, and fifth are. I do not consider G2 anymore because that's out of the game. And immediately I'm going to cross out anything further down which has not been selected in this round. And so I keep doing that. Maybe in the next round I'm going to have G3 and G5 and so on selected, and then in the last round maybe I have G3 selected, so I already crossed out G4, and so at every row I'm going to have the subsequence which will go to some number G3 and G4 and so on the corresponding xi values. Okay, so that's my first step. The second step is that out of these numbers I'm going to pick by a diagonal argument. So I'm now applying a diagonal argument. I'm going to pick a function gt, and on the i's of these x's it is going to take the following value, limit as m goes to infinity g of n m m. In other words, I'm picking the mth term of the m subsequence here. So let's see what that means. I'm picking the first term of the first subsequence. I'm picking the second term of the second subsequence, and I'm picking the third term of the third subsequence, which is somewhere out here, and then the fourth of the fourth, and so on and so on. Okay? What's the point in that? Well, the point is that if I now fix any xi and take m to infinity, then eventually if I look at, for example, x3, then I'm looking at the third row, eventually I'm going to start looking at the starred members of this subsequence. Notice that anything I go through here is selected later on. So starting from the third member of the subsequence, any index I select is actually circled in yellow on the third row. In other words, I'm starting from number 3. I am actually stepping through circled values on the third row, and therefore I am going to have a limit along the third row if I do this diagonal subsequence. We've seen this before with generating functions. It's exactly the same idea. So for every xi, or every I if you want, I will have a limit of this subsequence. So I managed to make a convergent subsequence at the same time for every I, and that's what the diagonal argument can do for me. So this is called a diagonal argument. Everybody sees the diagonal here, right? First of the first row, second of the second row, third of the third row, and so on and so on. That's why it's called the diagonal argument. Okay, so I have some simultaneous convergence of these on these xi values for this subsequence. Okay, and now I want to extend this. So far I defined the function gt on my dense subset T. So recall that I started with the dense subset T, which consisted of the x1, x2, and so on members. On those values I defined the function. So I want to extend this to R. Extend this to R by the following way. I'm going to define a function gx by taking the infimum of gt of y, where y is in T, and also it's strictly less than x. So x is any real number at this point. Take any real number, look at the infimum of these gt values for every y in the countable dense subset which exceeds x. That's my definition of a function gx. Okay? Now, so this was my first step, using the diagonal argument to define a function, kind of a convergent function on simultaneously all of t, and then extend this to R. Okay, now the second step is a couple of facts which you can check yourself. G is non-decreasing. Essentially, this is just inherited from the individual members of the G1, G2, and so on sequences. So G is non-decreasing. You can also check that this guy is right continuous. This is again a consequence of this definition here, and also right continuity of the G's. I'm not going to do that here as well, or either. Okay, and what we want to show now is that we have convergence of the G and M's. So this is going to be my subsequence, this G and M, this subsequence that I promised to calculate, this G and K. I'm now going to call this G and M. So I need a subsequence along which I have convergence to actually to this limit G wherever G is continuous. It's non-decreasing, so it will have plenty of continuity points. Fix one of these, so let Z naught be a continuity point, point of continuity, continuity point for this limiting G. And what I need to show is that the G N M M, so this diagonal subsequence of the G's at that point Z naught actually converges as M goes to infinity to the function G that I just defined at the same point Z naught. Okay, because that was the second part of this, so that's what we need to do, right? That along the subsequence we have convergence to some G right continuous functions wherever Z naught is a continuity point of G. Okay, so how does that work? Let's see how that works. Okay, so fix a point Y that's larger than Z naught and is in T. Okay, and let's take a look at the lim sup of G N M M, so this diagonal subsequence on Z naught as M goes to infinity. Now on this point Z naught, I have no idea whether I have convergence or not, or if Z naught is in T, then of course I do, but otherwise I don't necessarily, but I always have the lim sup. Okay, and because Y is larger than Z naught, and for every NM this function here is monotone, that monotonicity is going through the lim sup, and I have that if I now take G and M at Y, and Y is larger than Z naught, then I have an inequality surviving the lim sup. However, Y is in T, and in T I do have convergence of the G and M's, and the limit is GT. So this lim sup is going to be equal to the limit on T, and it's equal to GT of Y, just by definition of GT and the fact that Y is in T. Okay, now I'm going to take a lim inf of this inequality as Y is larger than Z naught. Lim inf for Y's larger than Z naught of this inequality. The left hand side of course doesn't have Y in it, so it stays being who it was. Lim sup G and M Z naught. The right hand side, if I take a lim inf, then a lim inf in all Y's from T above X will actually give me G of my value. This, whether it's inf or lim inf, it doesn't really matter because G is monotone, so you could actually replace the inf by a lim inf. And so I'm going to have on the right hand side, taking a lim inf of these guys over Y larger than Z naught in T, I arrive to G of Z naught, which is 1/2 of my inequality. What I want to show again is that the limit of the G and M Z naught is actually equal to G of Z naught. That's what I want to show, and I have half of it. So I'm now going to do the other half of it. The other half will work like this. So take now z1 smaller than y smaller than z naught, where y is in t, and z naught is a point of continuity of g, the limiting thing. Z1 is any real number. Okay. Now, what can I say about these? So take g of z1. G of z1 is obtained as the infimum of all y's in t where y exceeds z1. So if I don't take an infimum, just fix a particular y, then I'm just going to be larger than my infimum, larger and equal than my infimum. Now this is equal to the limit, by definition, as m goes to infinity, of g of nm and my. That was the definition of gt. Okay. Now y is smaller than z naught, so each of these g and m's is less than or equal than g and m of z naught, and that survives taking at least a lim inf. I have a limit here which is the same as the lim inf in that case, and therefore if I write a lim inf on the right hand side of the same expression except taken at z naught, then I have the inequality the other way around. Okay. However, now I want to make use of the fact that z naught is a point where g is continuous, and therefore if I start looking at the limit as z1 goes up to z naught of g of z1, then I must have g of z naught by continuity of g, because at z naught g is continuous. And if I now, on the right hand side, just plug in what I had in the previous row, every single member here is bounded by that lim inf, so that survives the limit as well, and this is smaller than or equal to the lim inf as m goes to infinity of g n m m at z naught, and at this moment I'm done, because what I found before is that the lim sup of the g and m z naught is bounded from above by g of z naught. However, the lim inf is bounded from below by the same g of z naught, so therefore lim sup equals lim inf equals limit equals g of z naught. So I conclude from here, from these two, I conclude that this limit exists, and actually is equal. This limit exists and is equal to g of z naught, and that's what I wanted to prove.